Hey guys, I'm back with a new video. In this video we are going to start with a new classification technique, and that is support vector machines. Now before we start understanding about SVMs in detail, we first need to have some basic knowledge of the terminologies revolving around SVMs. Now SVM is a supervised machine learning technique. So supervised machine learning technique. If you don't know what supervised learning is, the link for the video discussing the same in great depth can be found down below. Now let's first start with a geometrical figure that is very important for understanding the topic of SVM, and that is hyperplane. Now the concept of hyperplanes is relative to the dimensions that you are considering. So if you have a k-dimensional space, then your hyperplane will always be a k-1 dimensional surface. So hyperplane. So if you are present in 3-dimensional space, then your hyperplane will be a 2D plane. If you are in 2 dimensions, then your hyperplane will be a 1D surface, or you can say just a line. Now let us consider an example to understand more on hyperplane. Let us consider we have this 2-dimensional space where we have x-axis along the horizontal and y-axis along the vertical. So in this case, k is 2 because here we are having 2 dimensions. So in the case of 2 dimensions, our hyperplane will have dimensions that is 1 less than the dimension that our space is in. So our hyperplane in this case will be a 1-dimensional surface, and we know that the 1-dimensional surface is nothing but a simple line. So this is going to be our hyperplane. Now let us move one level up and let us consider a 3-dimensional space, and let us change this to 3. So let us say our 3 dimensions is like this. So x, y and z. So here we are having 3 axes, namely x, y, z. And for this case, our hyperplane will have 3-1 dimensions. That is, our hyperplane will be a 2-dimensional surface, or you can say that our hyperplane is a 2D plane. So let me help you in visualizing this. So it will be something like this. So it will be a 2-dimensional plane. So you can see that in this case our hyperplane is not a line but a 2-dimensional plane going through this 3-dimensional space. So in essence, if we know the dimensions of the space in which we are in, we can easily tell what will be the dimensions of the hyperplane. So now we are crystal clear about the visualization of a hyperplane in different dimensions. Let us move forward to the concept of support vector machine. Now as a side note, we can have any number of hyperplanes for the dimensional space we are in. So for this 3-dimensional space, we can have any number of planes. For a 2-dimensional space, we can have any number of lines. And all the hyperplanes in the space that we are in should have exactly the same dimensions. So if we have a 2D space, then we can have any number of hyperplanes for a 2D space. But each of these hyperplanes in this case must only have a single dimension, just as we discussed. I hope this makes complete sense. If you face any problem regarding this, feel free to ask in the comments section down below. So in essence, if we have a n-dimensional space, we can draw infinite number of n-1 dimensional hyperplanes for that n-dimensional space. Now let us consider a simplistic case where we are having a 2-dimensional space. So x and y. Okay, so let this be x1 and this be x2. So x1 along the horizontal axis and the x2 axis along the vertical. Now consider a hyperplane for this space. So our hyperplane, as we all know by now, will be a 1-dimensional surface, which is practically a line, right? And let us say the equation for our line is m1 x1 plus m2 x2 plus m0 equals to 0. Let me represent this line in the diagram. Let us say this is the line, and the equation for this line is this. So this equation represents the infinite number of lines that can pass through the given dimensional space that we are in. Now let us take 2 points in the given space. So first one right here, and let this be x1 star and x2 star, and let the other point be right here. So x1 double star and x2 double star. So I'm denoting these points by p and q respectively. Now let us put the coordinates of these 2 points in the given equation of line, which is one of the possible hyperplanes for our 2D space. So for p point, if we put the coordinates in this equation, m1 x1 star plus m2 x2 star plus m0, and this will definitely not be 0 because it is lying right in the area that is left to this hyperplane, right? So the value that we get after substituting these values of coordinates into this line equation will either be negative or positive, but definitely not 0. Now for Q point, we get m1 x1 double star plus m2 x2 double star plus m0. So the value that we get after substituting these 2 points in this equation will definitely not be 0 as well. So if this value is negative for Q point, then this value for P point should be positive, right? So the result for each of these 2 points getting substituted into this equation will either be negative or positive, but definitely not 0, because these 2 points are not lying on this line that we traced. So you will get one negative side and one positive side. So if this side is coming out to be negative, then this will be positive, or if this side comes out to be negative, then this will be positive, right? So this way we are able to separate the points of the two classes, but there is a lot that goes in finding this optimal line, and let us see how we can derive such an optimal line in the second part of this video. So our end goal is to find the best possible line that can distinctively separate the two classes that we have in case of a binary classification, where we have a two-dimensional space or two classes, or in general to find the best optimal hyperplane that can separate the classes that we have in the best possible manner. So now let us understand the working of SVM in a bit detail. Let us consider the case of binary classification where we are having two classes, x1 and x2, and let us say the points of these two classes are represented by hash and asterisks. So let me use red shade for the first class points, and let us use asterisk for the second class points. And let us draw three possible hyperplanes to separate these two classes from each other. So let us say first one is this. Let us say second one is this. And let us say the third one is this. And let me label this by A, let this be B, and this as C. Now here we have three possible hyperplanes, and we are making them pass through our two-dimensional space like this. So our main goal is to find the best optimal hyperplane out of these three hyperplanes that we just traced that best classifies the two classes. So here you can see the hyperplane B does a better job than other two hyperplanes. If you consider hyperplane C that is passing through these 2 points, so it is definitely not doing a perfect separation. And same for A as well, so it is passing through this point, but B does a perfect demarcation, or you can say a perfect separation between these two classes of points. So B is the optimal one here. So now let us move forward and let us understand now about classifier that uses SVM, called as the Maximum Margin Classifier. Now there are cases as well where we cannot make use of the Maximum Margin Classifier, and we will discuss them later. So let us discuss about the Maximum Margin Classifier now in great depth. So Maximum Margin Classifier. Let us again consider the same example, and then we will see how margin comes into picture to help us in understanding why B was the best classifier in that case. So let us consider our simplistic case of binary classification where we have two classes. For first one, let us represent the observations by using asterisk, and let us represent the observations of the second class by using hashes. And let us take three of the possible hyperplanes from an infinite set of hyperplanes. So let us say the first one is this, and let us say we have one asterisk here as well. Let us say the second hyperplane is this one, and let us say the third one is this. Now in this example, as you can see here, it is difficult to tell which one of the three is the best possible hyperplane, because each of these three are doing perfect separation of both the classes. Now here comes the concept of margin that will help us find the best out of these three. So as I already told you that for an n-dimensional space, we can have any number of n-1 dimensional hyperplanes. Here we are considering only 3 such possible hyperplanes. For this case, where we are having 2-dimensional space, we can have any number of 1-dimensional surfaces. We are considering only 3 of them. And our prime goal is to find the best possible line that can distinctively separate both the classes of points in the best possible manner. So by just seeing this diagram, it is very difficult to tell which is the best out of these 3. So let us now understand the concept of margin by taking a fresh diagram. So let us say this is our axis x1, x2, and let us represent the points of our first class by using hashes. And the points of second class by using asterisk. And now let us say we have this hyperplane that is separating points of both of our classes from each other. So for calculating the margin, the very first step is to find the perpendicular distance of each of the points that we are having in this entire 2-dimensional space relative to the hyperplane. So what is the margin here? Margin here simply means the smallest distance between the hyperplane and training observations. So let me write this down. Smallest perpendicular distance between the hyperplane and the training observations. Let us consider some of the points and drop a perpendicular from those points on the hyperplane. So this. Now this perpendicular is the margin, and this is at a right angle relative to the hyperplane. Now let me drop one here as well. Then this one. Let us say this one. Then say this one, and you can draw for these 2 points as well. Let us go to the other side of the hyperplane and do the same as well. So this, and say this as well. Now can you tell me what is the margin in this diagram based on this definition? So you can see this point, which is represented by asterisk, this one is closest to our hyperplane, and therefore the perpendicular distance of this point relative to the hyperplane is this distance, right? So basically this is the point whose perpendicular distance from the hyperplane will be considered as the margin. So this distance is the margin. Now let me draw 2 fresh diagrams and understand how to find a classifier that best separates the 2 classes, taking this concept of margin into account. So let me draw the first diagram and let us define the points of our classes. So the first class by hashes and the second one by asterisks. So let us use the red color, and now let us replicate this diagram right here. So first the hashes and now the asterisks, and let us draw our hyperplane. So let us say the first hyperplane is this, and the second one is this. So can you tell me what will be the margin for both these cases? So for the first one, the margin will be this, because this is the point that is most closest to this hyperplane, and the perpendicular distance from this point to the hyperplane is the smallest, right? So this is margin m1, say. And if we talk about this diagram, here the smallest perpendicular distance is this. So the margin for this diagram is m2, because this point lies closest to the hyperplane, and therefore this point will give us the smallest perpendicular distance relative to the hyperplane, right? And from these 2 diagrams you can also see that margin m2 is smaller compared to margin m1. So for maximum margin classifier, if we have many hyperplanes passing through our 2D space, the best hyperplane is one which maximizes the margin property. So can you now tell which one is the best hyperplane out of these 2? So since we want to maximize the margin, therefore we choose hyperplane 1 and not 2. So this is h1 and h2. So we choose h1 over h2, right? So now we have selected the margin for our classifier. Now let us take the same margin on the other side of the hyperplane. Let this be a units. So this will also be a units. So now you can see that the hyperplane is now the midline between the widest gap that we have in between our 2 classes. So let me use a dotted line right here. and let us use this color. So here you can see the widest gap is 2a and the hyperplane is passing exactly midway of this distance. So this is a and this is also a. Now one other thing, that these 2 points, this one and this one, are closer to the hyperplane and they help in influencing the position and the orientation of the hyperplane. So these are called as support vectors and they play a key role in helping us build our optimal classifier. So let me write this down. So this one and this one, these 2 points are called as support vectors. And the midline of this gap that we got in this case is the maximum margin classifier, and any other line is far away from this line and far away from being called as the maximum margin classifier. So this is not a maximum margin classifier, but this is one. I hope everything makes sense now. So now we know a lot about SVM and the maximum margin classifier. Let us move forward to the next topic, where we will discuss about how we can separate two classes which are not perfectly separable by using a classifier called as the support vector classifier. Let's catch up in the next one.